Mass-energy equivalence. E equals mc squared is the most well-known equation among non-professionals. It relates the energy, E, of a particle to its mass, m. Before we further discuss this relationship, let's talk about what energy and mass actually are. Energy is the scalar quantity that remains constant over time in closed systems, as opposed to momentum, which is a vector quantity. Systems and particles have energy due to their motion in the form of kinetic energy, and due to their position in a force field, like the gravitational or magnetic fields, in the form of potential energy. So, what is mass? Contrary to popular belief, mass is not the amount of matter in an object. Another word for mass is inertia, or the tendency of an object to resist being accelerated. Thus, objects with higher mass are harder to move than objects with lower mass. In 1905, Einstein published Does the Inertia of a Body Depend Upon Its Energy Content?, where he derived the relationship between energy and mass using special relativity. In the paper, he proved that objects have energy due to their mass even if at rest and in no force field. We call this energy the rest energy. The rest energy E is directly proportional to the mass by the speed of light squared. This equation shows how mass is another form of energy. This is never observed at our level in the macroscopic world, but is commonplace at the atomic scale. Let's take a look at the nucleus of an atom, which is a combination of protons and neutrons. The protons and neutrons are bonded to each other due to the strong interaction, which is a powerful attractive force. During their formation, nuclei lose energy to their surroundings. Because the total energy of the system, the nucleus, was decreased, the mass of the system will also decrease due to mass-energy equivalence. The amount by which the mass decreases is called the mass defect. The loss of energy during the formation of a nucleus is also the energy needed to break it apart. We call this the binding energy. To calculate the binding energy, we simply multiply the mass defect by the speed of light squared according to Einstein's equation. In AP Physics 2, this is the only situation in which you encounter mass-energy equivalence. Alright, so here we're given that the sun radiates approximately 4 times 10 to the 26 joules of energy per second, and we're asked to find how much mass is lost. So due to mass-energy equivalence, we know that as the sun is losing energy, it's also going to be losing mass. We can find this relationship by manipulating Einstein's equation, so we get m is equal to energy over the speed of light squared. Just plugging in the numbers there, we'll get 4.4 times 10 to the 9th kilograms, and that's per second. So every second, as the sun's losing 4 times 10 to the 26 joules of energy, it'll also be losing 4.4 times 10 to the 9th kilograms of mass. Now on to the second part. Given that the sun starts out being 2 times 10 to the 30th kilograms, we're asked to find out its lifespan. So to find the lifespan in seconds, you're just going to take that initial mass and divide it by the loss per second, and that will give you its lifetime in seconds. So plugging in the numbers there, you'll get 4.5 times 10 to the 20th seconds, and dividing that by 60, and then by 60 again, then by 24, and then by 365, you'll get approximately 1.44 times 10 to the 13th years. Okay, so for the second problem, we're given a carbon isotope and told it has a mass of 12 atomic mass units. And we're first asked to calculate the mass defect. So looking at this isotope, we see that it has 12 nucleons from the mass number there, and we see that it has 6 protons from that atomic number. So if there are 6 protons and 12 nucleons total, there must be 6 neutrons. So the mass defect is simply the mass of the isotope and the predicted mass of the isotope minus the mass of its components. So plugging in the numbers there, 1.002726 is the atomic mass unit mass of any proton, and 1.00866 atomic mass units is the mass of a neutron. So plugging in the numbers there, we'll get the mass defect of approximately negative 0.0956 atomic mass units. Now to calculate the binding energy, and we're asked to do it specifically in mega electron volts. So C squared is equal to 931.49 mega electron volts over 1 atomic mass units. That's just the definition. if you actually to take the root of both sides, you would get the speed of light in meters per second on the right side there. So E is equal to the mass defect times the speed of light squared, and we already have the mass defect from part A. So we're just going to substitute in the 931.49 mega electron volts over 1 atomic mass unit into C squared in Einstein's equation and plug in the mass defect, and we'll get approximately negative 89.065 mega electron volts for the binding energy. So for this last problem, we're asked to calculate the energy released in the first fusion reaction in the Sun, and we're given these deuterium and protium. So just to clarify something here really quick, both of these are just hydrogen isotopes, so the only difference is the number of nucleons that they contain. They both have the same amount of protons, but deuterium has one more neutron. So the mass defect is the first thing we have to calculate in solving this problem, and the mass defect is simply the mass afterwards minus the mass before. So before the reaction, we have 2 protiums, so that's what we're subtracting, so it's 2 times the mass of a protium isotope, and then we're adding the mass of the deuterium and the mass of the electron that's created as a result of the reaction. So plugging in the numbers there, we'll get approximately negative 0.0011 atomic mass units for the mass defect. And then using the same thing as we used for C squared in problem number 2, we're going to substitute in 931.49 mega electron volts over 1 atomic mass unit for C squared. And we're going to get approximately negative 1.0256 mega electron volts as our final answer for this last problem.